Well, let's continue from the previous video with another example. So let xy be associated with the ordered pair x prime y prime if and only if f of x prime is 2x. F takes y prime as equal to 3x. Another way of writing it, I think a better way of writing it would be, here's the function f. And it's going to take an ordered pair xy, and it's going to compute an x prime and a y prime. X prime is 2x, y prime is going to be 3x. That's a nicer way of writing it. So again, once we have f of xy is going to be x prime y prime, which is 2x, 3x. A much simpler way of writing it, I think. Either one, these are both better ways. Well, let's find the images of these 3 points. So for the first one, the xy value is 1, -1. So I'm going to use the function. This will be very simple. F of 1, -1. X is 1, y is -1. What's my x prime, y prime going to be? My x prime is going to be 2 times x. My y prime is going to be 3 times x. Well, x is 1, so it's going to be 2, 3. Notice it has nothing to do with the y value. The image value has nothing to do with the y value. Next one, f of 1/2, 1/3. Okay, the x prime, y prime, given that x is a half and y is a third, it's going to be 2x, 3x. Well, what's 2 times x? X is 1/2. 2 times that is 1. And then 3x. What's 3 times 1/2? Well, that'd be 3 halves. Okay, and now let's find the image of -3, 4. The x value is -3, the y value is 4, and we need to find x prime and y prime. And we find them by 2x, 3x. So what's 2 times x? That looks like that's -6. And then what's 3 times x? That'd be -9. Okay, pretty simple, straightforward, just found images of 3 certain given points. Now let's find the pre-images of these 2 points. So these are like our x prime and y prime. Let's find the x prime, y prime, x prime, y prime. Let's find an ordered pair that maps to these numbers. And it might be obvious. 2, -3 has no pre-image. That means there's no numbers, no ordered pair that maps to 2, -3. And why is that? Well, if you look from the previous example, I think we've convinced ourselves that every image, every x prime, y prime, is 2 times x, 3 times x. So that means that every ordered pair is going to be of the form 2x, 3x. Let me write that down. All images, the ordered pairs that get mapped to, have the form 2x, 3x. And if we wanted to, we could divide them both by 2. And it could have just said x, comma, half of that would be 1.5 x, 3 halves x. These are the same sets because they're true for all values of x. And notice that's true over here. We have 2 and 3. 2 times 1, 3 times 1. We have 1, 3 halves. That's 2 times a half, 3 times a half. -6, -9, that's 2 and 3, both multiplied by -3. Okay, so there's no way to get an image of 2, -3. We can get 2, 3, we already did that. But we need them to be of the form 2 times a number, 3 times a number. And the number has to be the same number, 2x, 3x. Okay, Notice F maps every point of the form 2 comma anything. So I'm just going to say 2 comma y. It does not matter what y is. What does every point of this form get mapped to? X is 2, y can be anything. Well, it doesn't matter what y is because y is not used to compute x prime and y prime. So 2 is going to be, if x is 2, it's going to go 2x, so it's going to go 4. And then what's the next one going to be? 3x, which is 6. So we've got infinitely many points being mapped to this one single point. It doesn't matter what the y value is because y is not used in the function up here. Y is simply 3 times x, where the x prime is 2 times x, y prime is 3 times x. So I could say, kind of to finish this one off, f of 2 comma y is equal to 4, 6. Y can be any real number at all. And you'll get mapped to 4 comma 6. So the pre-image would be all of these numbers, 2 comma 1, 2 comma 0, 2 comma negative 5, 2 comma pi, 2 comma 10. They all get mapped to 4, 6. Okay, the question is f defined up here a transformation? Hopefully you said no right away. It is neither 1-to-1, because we have infinitely many numbers, ordered pairs getting mapped to this one, so it can't be 1-to-1. And it's also not onto. It's neither 1-to-1 nor onto, because here's an ordered pair, 2, -3, that doesn't get mapped to. So the function is not onto. So it's not a transformation. Good example. Okay, rather simple lemma, a bijective inverse lemma. Let f going from p into p be a plane function. Well, in this case, the p might be the plane, might be the xy plane. F mapping the plane into the plane, it's a plane function. If that's true, then f is bijective if and only if f inverse exists. That, I think we've seen that before in other classes. The definition of a bijective function, well, one definition is it has an inverse function. If it has an inverse function, it's bijective. Here's a theorem. The inverse of a linear transformation is a linear transformation. So if f is a linear transformation, its inverse will take the points over here and map you back into this one, and that would be also a linear transformation. Another fact about linear transformations is that the composition of two linear transformations is a linear transformation. And we'll talk more about linear compositions of linear transformations later. And we're going to end up this video with a definition of an identity mapping. A plane transformation is the identity mapping. Basically means whatever number you put into the function, its own identity comes out. The same value comes out. If every point in the plane is a fixed point. Remember, fixed point means f of q equals q. If that's true for all points in the plane, then it's just the identity mapping.